energy and dark matter, and today she presents the topic entitled Interaction in the Dark Sector. Daniela, este espacio es de usted.
Muchas gracias. Voy a presentar entonces. Ok, ¿se ve la pantalla?
Sí, todos podemos visualizar.
¿Y si paso las slides también?
Sí, también.
Ya, perfecto. Muy bien. So this talk will be in English, right?
Yes, please.
Yeah, okay. So, well, thank you very much for the invitation and congratulations for this very amazing meeting. My name is Daniela Grandón. I'm a PhD student in Universidad de Chile. And I will present Interaction in the Dark Sector based on these two papers here in collaboration with Dr. Víctor Cárdenas from Universidad Valparaíso in Chile and Dr. Samuel Lepe from Pontificia Universidad Católica Valparaíso. They are here, so hello to them. So let's start. So my work is about cosmology. So I will briefly introduce you the main ingredients of this topic. The standard model of cosmology is called LCDM, and this is the simplest model that fits or explains observational data very well, and tell us that the universe is made up of ordinary matter in a 5%, which is baryonic matter, matter that we know and we can see, like dust or gas of this astronomical image that we have seen. And we have in a 27% a form of exotic matter, whose nature or origin we don't know, but we know its existence because of the gravitational effects is produced on large-scale structure. For example, we have gravitational lensing. And finally, we have another form of energy, which is called cosmological constant or dark energy, and that covers 67% of the total content of energy in the universe. So this form of energy fills all space and is responsible of accelerated expansion of the universe because it acts against gravity at large scales. So these are the principal ingredients, and to understand better this model, let us study two historical discoveries of modern cosmology that settle down the model. So here in the left picture, we have the cosmic microwave background radiation, or CMB. So this radiation comes from the early universe, when the universe was something like 380,000 years old. And in that epoch, the universe was a soup of electrons, protons, and photons colliding, interacting at a very high rate. And these collisions produce that photons cannot travel freely through the universe, right? So the expansion decreases and the temperature of the universe falls to a point where these collisions are no longer efficient. So electrons and protons combine in nitrogen atoms and photons can escape and travel freely through the universe. So these photons are the radiation that we are seeing in this picture. Those photons are responsible of this cosmic microwave background radiation. And this is a picture of the universe when the universe was young, right? So the first satellite that measures this radiation is COBE at the beginnings of the 90s. And what measures first is the black body radiation of CMB. So the early universe was in thermal equilibrium, and also it measures this radiation in all directions. And COBE found that the radiation is isotropic. In all the directions, you have the same intensity. Of course, you have fluctuations, but they are very tiny fluctuations. And in this picture, they are magnified, are of the order of 100,000. So in general, it is a very uniform radiation. So on the other hand, we have here the supernovae plot, where in 90s, at the end of 90s, two collaborations measured supernovae's apparent magnitude at different redshift, and they found that these objects were dimmer than expected from theory. So the simplest explanation is to include a component of energy in our model called cosmological constant or dark energy that produces the accelerated expansion of the universe. And because of this effect, you can see this dimmer apparent magnitude for this supernova. So in this picture, you can see this black line. This black curve is a model without cosmological constant or dark energy. And you can see in a high redshift objects, this curve falls below the data points. So it doesn't describe the data very well compared to the blue curve, where you can see that it fits the data with high precision. So these are the very important facts of modern cosmology that says that the universe is isotropic and homogeneous in an expanding phase. Now, the metric that includes all these features, homogeneity, isotropy, and expansion, is the Friedman-Lemaitre-Robinson-Walker metric, where here you can find a function that depends on time, and this describes the expansion. Here you have a K factor, which describes the curvature of the universe. And when universe is flat, you have a K equal to 0. And also you can find this Hubble function, which measures the expansion rate in the universe by considering the derivative of the K factor with respect to time. So if now we introduce this metric to the Einstein equations, what we get are the two Friedman equations. And these are very important equations. We will see this equation and this one in the next slides of my presentation. This expression tells you that the expansion rate of the universe depends on the total energy content of your universe. So for example, if in your universe dominates radiation, you will have a specific expansion rate, which will be very different if your universe is dominated by matter, for example. And this term is in general negligible because data tell us that the curvature of the universe is flat. So you will, in general, you will see that this term goes away. And this is the acceleration equation that relates the acceleration of this expansion rate related to the energy and pressure of the universe, of the fluid that composes this universe. From Einstein equation, you can find also this continuity equation. Sorry if this is in Spanish, but I prepared some slides in Spanish and in English. This is the continuity equation. This comes from Einstein equation as well. And this describes the energy conservation of your fluid in the universe. Okay, so as we are working in a flat universe, we can define this density parameter that describes what is the fractional energy content of your specific fluid. So we've defined this density parameter for matter, for cosmological constant, and radiation. And the first Friedman equation with this definition takes this form, okay? Where this extra term here is the cosmological constant that we introduce to explain supernova data, okay? And this is the Hubble function for lambda CDM, where lambda stands for cosmological constant, whose equation of state is equal to -1. But we can relax this assumption and generalize cosmological constant to a fluid, which we will call dark energy. And in that case, we get this expression where the equation of state is different from -1. It's constant, but could take other value. So if you introduce the equation of state -1 in this model, you recover lambda CDM. Okay, so okay, we see that this model fits data very well, but there is a problem, serious problem, and the main one is that we have two energy components that we don't know the nature of them, but they are only introduced to fit data. But we would like to know more information or the nature of which particles are related to these two fluids. And also we have these coincidence problems. And this shows that we are in a very special moment of the energy of the universe evolution, sorry. So here you can find a plot where the horizontal axis is redshift. So redshift equal to 0 is equal to the present, and as redshift increases, we are going back to the past. So if theta is very, very large, we are looking at the universe when the universe was a baby, for example. And this is today. So here you can see these curves that for the first 1,000 of years, the dominant component is radiation, and then matter with orders of magnitude of difference between dark energy. Yeah, so dark energy is smaller by a lot of orders of magnitude, but at redshift equal to 0.5, more or less. And here we can see that the universe is dominated by dark energy, but with a fractional density very similar to dark matter. So this tells us that we are kind of in a very special moment of the evolution of the universe. So, and we don't like to be that special. So this is a problem. It's one of the main problems of the LCDM model. And also, if you want further information, I really recommend you to read this paper. It's a very interesting paper. And so we have a lot of problems here, and we need to look for solutions. And one family of solutions consider dark energy as a dynamical quantity. So is that the equation of state or energy density evolves with time. And among these models, we find interaction in the dark sector, which is the energy transfer between dark matter and dark energy, where both components interact. So these models solve some problems of the standard model, but also I think it's very logical, because you know that the standard model particles interact between each other. That's what we see through thermal evolution of the universe. So why these two components could not interact as well? And as we completely ignore the nature of both components, we can think that they are somewhat related. So let's go with interaction. Okay, so here we have these continuity equations. This is for cold dark matter, and this is for dark energy. And if you remember a few slides ago, we saw that this is equal to 0 and this is equal to 0. So this means that they conserve separately and together also. And these interaction models, what they do is to introduce this function Q, or this term, with opposing signs in order to conserve energy when you sum up these two equations. Okay, this is a phenomenological approach, because from physical principles, we don't have a form or a preferred form for this function. So what we do usually is to propose a model for Q, propose a function, we will see in details in the next slides, and test them with the data and see what data tell us about this interaction scheme. So if Q is less than 0, there's energy transfer from dark matter to dark energy. And if Q is more than 0, we have energy transfer from dark energy to dark matter. So in this work, we use these three models. This model depends on the Hubble function, the density, the energy density of dark energy in this case. In this case, we call dark matter. And this gamma value is a free parameter that we want to constrain. And this value describes the interaction or the coupling between these two fluids. And in this third model, we have now alpha. Alpha will be this free parameter we want to study. And it depends also on the sum, the derivative of the energy densities. So, okay. And so, considering this coupling between these components, we can get this form now for the Hubble function. This first Friedman equation that we saw before can be written in this form with this interaction scheme. So E is the Hubble function, okay? Don't worry, it's the H, but it is divided by H naught. So it's another form to write the same equation. And here you can see your coupling parameter If gamma is 0, you recover omega CDM model, where you have a dark energy with equation of state omega. In that case, if this is 0, this goes to 1, and you recover that model. And the same for model 2. You can recover omega CDM, setting this to 0. So these are the expressions for these two models, and the free parameters are the Hubble constant, the energy density of baryons, energy density of cold dark matter, and the equation of state at this gamma parameter. And here for the third model, we have a more complex function, but don't worry, you just have to focus on beta, because beta includes this interaction term, and depends on this other function that depends on beta as well. Okay, so now we have the models, we have the equations, the theoretical side of this, and we want to test these models with observational proofs. So the observational data we will use is measurements of the Hubble function. And for this data, what they do is, some galaxies form or were born at a specific, at the same time, or at a specific epoch. So if they were born at the same time, you can think they should have the same age. So you measure the age of these objects, and you measure the difference in redshift. So the ratio between the difference in age and in redshift is a roughly estimate of the Hubble function. We use also supernovae data. Well, that was what we described before in the first slides. So you measure supernovae type 1a at different redshifts, and you measure the apparent magnitude, and this gives you information about the underlying cosmological model. We also have Bionic acoustic oscillations. This is like a standard ruler or a typical scale that you can find in your distribution of galaxies in the universe. So here you can see a lot of galaxies, and you see like a pattern here, like in a ring. And this is a typical scales that remain fixed in co-moving coordinates. And this also gives us information about cosmological parameters. We also measure the gas mass fraction in clusters. You can measure the total matter of clusters using X-ray or optical observations, and you measure the mass content of baryons. So this ratio between baryons and total matter also can give you information about cosmological parameters, because this should be constant. And measurements from CMB. We measure some typical scales or distance related to the angular power spectrum of CMB. And these are the 5 cosmological proofs. Typically, these are considering low redshift observations, also this one, and these are like high redshift data. So we use this package MC from Python to make the statistical inference, and this MC is a Markov chain Monte Carlo method that what you do is you sample your parameter, your space parameters, and you try to reconstruct the posterior probability distribution for the cosmological parameters we are studying. So let's go with some results. So for the first model, here we can see our best fits. A, B, and C stands for different combinations of this observational data. So for example, C is the combination of the 5 cosmological proofs. A is for only 3 of them. And the best fits of the standard model are these values. So you can see there's an agreement in the Hubble constant, also in the density of dark matter. But what we are interested in is in this gamma. So for example, here gamma is 0.03, but if you look up the error bars, you can see that there is no sign of interaction, because you can get the 0 from this lower limit. So you can imagine your contour plots, your 0 value is inside this 1 sigma contour. So this is telling us that there is no interaction in this specific combination of data. But if we look at C, which are the 5 cosmological proofs together, we can see a positive evidence of interaction. This value is positive, so that's one point. And also it is 3 sigma away from 0. So it excludes the standard cosmological model LCDM at 3 sigma, which is a very, statistically speaking, is kind of evidence that there could be an interaction between these components. For the second model, we can see more or less the same. For example, A is the same cosmological proofs, the same combination, and here you can see the error is compatible with 0 gamma. But in the case of the 5 cosmological proofs, you get also evidence for interaction, and also you get the same sign for gamma. So that's very important. And for the third model, we test different other combinations of data. This is the ones that we saw in the previous models. So it's clear that here we cannot find evidence for interaction. For example, this gives 0, and this gives also values that are consistent with 0. So this alpha value is equal to 0, roughly speaking, or statistically speaking. And in these other combinations, you find evidence, but here we are only considering data from low redshift observations. So low redshift observations maybe can, or not maybe, but they say that there could be interaction in this particular model. Okay, so discussion. So far, we have reported the results of analyzing 3 interaction models between dark energy and dark matter using 5 observational proofs. And using the combination of all the data, the first 2 models show positive evidence for the interaction, implying a transfer of energy from dark energy to dark matter. So, okay, but we have studied this interaction scheme in a phenomenological way, but we would like to know what physical principles tell us about this interaction scheme, right? So we will go now to study thermodynamics in an expanding universe. So using a single fluid in an homogeneous and isotropic universe, a flat universe, we find these equations. Okay, this is the Hubble equation of Friedman equation we saw before. Here you can find some constant. The only difference is the constants, and also the chi term it goes away because we are working in a flat universe. So this conservation equation for this single fluid that lives in this universe can be written in this way. So we try to rewrite this equation in a more common or usual way that we saw in our courses of classical mechanics or thermodynamics. So this is the energy, and this is equal to 0, right? But we are working in a adiabatic expansion, so we turn on this term, okay? Just remember to the second law of thermodynamics, and we turn on this term to see what entropy can tell us about the physical quantities related to the single fluid. So if we rewrite this expression in this way, we can get this result. So this tells us that this combination of parameters is constant. And it's constant through the evolution of the universe, because this depends on time, and this temperature could depend on time too. So now what we want to do is, okay, we have this interaction. So in the future, what we want to do is to check how temperature of these components evolves with time. So entropy will help us in this task. So for this single fluid universe, we can find these 2 expressions for the temperature. In this case, the equation of state is constant. It could take any value, but it's constant. But in this other box, the equation of states could depend on time or redshift. So when the equation of state evolves with time, you can get this other expression. See, if this is constant, you recover the left equation. So now let's go to a more realistic case. Our universe is not filled with only one fluid. Let's go to two fluids. So for two fluids, we have our conservation equation, right? For dark energy and for dark matter in this case. And we want to see what happens if we consider lambda CDM, where the equation of state for lambda is equal to -1. What temperature can be associated to this lambda fluid? So we took these previous equations and we can write them in this form. And the result is this very important relation. So for lambda, this equation of state should be -1, well, is -1. So this left term goes to 0. This implies that this right temperature term should be 0. And that is a problem. So from a thermodynamical point of view, the model lambda CDM with two fluids shows that there is a 0 temperature for the dark energy fluid, which is inconsistent with thermodynamic or with physical principles. So from this point of view, lambda CDM is in trouble again because it gives these very awkward results. Now let's go to interaction. So now we include the Q term here. And as the Q term here is related to the differential of entropy, we can rewrite this Q in this form, right? Because we turn it on this term. So the evidence shows that Q is positive. This is the result we get in our paper, but also you can find very similar results for other models of other papers. So if this is the case, then the change in entropy for dark energy is negative, which implies that this, or not implies, but on the other hand, you have that matter, the change of entropy matter is positive. So this equation are telling us that the entropy for each component is not constant, but it should be constant for the composed fluid of these two components. And also you can find the details in this paper here. Yeah. So if we now play with this equation and some algebra, we find that the sum of these two entropies of these two fluids is different from constant, but we expected that it should be constant, right? So here we are in a problem because in interacting scheme, we find that the universe expands non-adiabatically, and that's a problem. So this opens a research area where there's more work to do in this topic. And also we can play with the same equations. And as this is more than 0, we find that for a positive evidence of interaction, also when Q is positive, what you find is that the temperature of matter through the evolution of the universe is always cooler or is less than the temperature of dark energy. So this is a very interesting result. So that in any instant, dark matter is cooler than the dark energy component. So to finalize my presentation, here we will study a specific model of interaction. So you have these equations that show interaction between these components, and you assume that the equation of state of lambda is -1 and cold dark matter is 0. This is the standard approach indeed. So you get this result for the continuity equation of dark energy and this for dark matter. So this shows that dark energy evolves as the integral of the coupling term. And this is a very interesting result because we have seen in other works that there is evidence that dark energy density evolves with time, and you can reconstruct this evolution with redshift. So if this is the case, this is a clearly sign that interaction is there. There is a sign of interaction indeed. So conclusions. We find positive evidence of interaction between this component using 5 cosmological proofs. We find an energy transfer from dark energy to dark matter. And from thermodynamical arguments, this implies that the temperature of cold dark matter is always cooler than dark energy. And it is also good to study dark energy models from first physical principles, for example, thermodynamics, because we saw that lambda CDM model is not consistent with with thermodynamics. So thank you very much.
Muchísimas gracias a Daniela Grandón por la presentación, excelente. Si alguien tiene alguna pregunta, puede levantar la mano. Ok, vemos que ya tenemos preguntas. Víctor, puedes prender tu micro en todo caso para poder formular tu pregunta.
Hola. Una consulta general. Bueno, yo he estado metido ahí en el tema, pero respecto a este aparente problema de que no tenemos expansión adiabática, que no sé, ¿qué cosa, por qué crees que sucede, digamos, o qué se puede hacer a partir de ahí?
Sí. Bueno, primero una reflexión, repasando un poco la presentación. Nosotros consideramos primero un universo muy idealizado, pero bueno, consistente con las observaciones, donde solo hay un fluido, y eso ya es un caso bastante ideal, y luego saltamos a dos fluidos. Y a partir de los dos fluidos nosotros esperábamos que la expansión sea adiabática, y no es el resultado que obtenemos en interacción. Pero es un caso muy simple porque nosotros deberíamos considerar también o sea, la contribución en la entropía desde otras componentes. Ahí no tengo mucha experiencia con ese tipo de trabajos, pero sí he visto que hay gente que considera entropía desde el mismo campo gravitacional. Probablemente hay muchas cosas que estamos ignorando en el análisis y que deberían ser estudiadas desde un punto de vista más teórico. Porque, por ejemplo, cuando uno estudia los sistemas desde el lagrangiano, uno lo que considera en general es un término de interacción o de acople entre las componentes, y quizás complejizar el análisis a ese nivel, que o sea, no sé si es tan complejo, pero estudiarlo a ese nivel podría contribuir a ver qué es lo que está pasando realmente con eso.
Sí, tenemos también una pregunta de David Camarena. ¿Puedes prender tu micro para poder formular la pregunta?
Gracias. Muchas gracias por la charla tan interesante. Yo tenía algunas preguntas con respecto a la primera y la segunda parte de la charla, pero creo que la pregunta que era respecto a la segunda parte ya fue respondida. Justo quería comentar que creo que es importante también tener en cuenta la contribución de las demás componentes del universo a la hora de calcular o de hablar de la entropía del universo. Pero en la primera parte sí tengo algunos comentarios y dudas. Estaba revisando los trabajos, los papers en los cuales están basados tu charla. Me parecen muy interesantes. Pero la primera cosa es que no termino de entender es si puedes usar realmente estos datos de la fracción de gas en los clústeres de galaxia para modelos de interacción. Porque estos datos generalmente asumen un perfil de densidad para las galaxias que es estándar, que no toma en cuenta la interacción entre materia oscura y energía oscura. Entonces, por ese lado tal vez hay un poco de inconsistencia, la verdad no lo sé, pero se me vino a la cabeza eso. Y otra cosa es que creo que para poder decir o llegar a concluir que existe evidencia para interacciones, es importante tener el análisis completo de los datos, por ejemplo, incluir las perturbaciones y calcular el espectro de potencia completo, porque los priors de la CMB no llegan a captar totalmente todo el poder de la CMB, especialmente si estás con modelo de interacción, y también incluir un análisis bayesiano un poco más profundo, como por ejemplo ver cuál es la evidencia bayesiana o calcular los cuadrados y la diferencia para llegar a una conclusión que esté de alguna manera soportada por lo que los datos indican.
Sí, bueno, respecto a lo último, creo que en el paper de termodinámica tú puedes encontrar los test estadísticos para los modelos que estudiamos. Ahora no recuerdo cuál era el favorable respecto al VIC o el AIC, pero ahí puedes encontrar esa información también, que no la puse. Y claro, lo que dices es bastante cierto, que tenemos este problema con los datos. Y de hecho, cuando uno quiere hacer reconstrucciones no paramétricas de alguna cantidad, por ejemplo, la evolución de la energía oscura, hay que tener harto cuidado de que tus datos no dependan del modelo. Y eso es algo que, bueno, se discute hoy en día, que en CMB o incluso en las observaciones acústicas, tú para calibrar estas observaciones sueles usar un modelo cosmológico lambda CDM para calcular ciertas cosas. Entonces, ese es un problema en que realmente se tiene que trabajar en detalle. Pero en este caso, como nosotros estamos estudiando desviaciones de lambda CDM que sean pequeñas, porque lambda CDM describe bien los datos, entonces no queremos irnos tan lejos tampoco. Podría permitirse incluso que estos datos de alguna forma dependan del modelo, y es bastante interesante porque en general, por ejemplo, CMB y BAO, que dependen un poco del modelo, cuando nosotros los sacamos del conjunto de datos para restringir parámetros, cambian de forma notable los constraints. Así que es un punto muy importante el que tú dices. Estoy totalmente de acuerdo.
Solo para finalizar, porque sí estoy de acuerdo con lo que tú dices, es muy importante tener en cuenta cuál es el modelo fiducial que se está usando, si esto afecta a los datos observacionales de verdad. No creo que sea el caso completo de CMB, porque una vez tú tienes o calculas el espectro de potencia completo, puedes de alguna manera liberarte de ese fiducial, o que hay otros sistemáticos que vienen de fiducial, pero no hay realmente un indicio de que eso pueda afectar. El caso del BAO sí es un poco más delicado. Estoy completamente de acuerdo con eso. Bueno, y creo que básicamente era eso. Gracias.
Gracias.
Ok, también tenemos una pregunta de Samuel. ¿Sí? ¿Puedes prender tu micrófono?
Hola.
Hola, ¿me escucha?
Sí, súper.
Hola, Daniela.
Hola, Samuel.
Excelente, bonita tu presentación. Daniela, en las tablas 1 y 2, los valores para el parámetro de ecuación de estado omega no tienen chance nula, ¿cierto?, de ser menores que -1.
Phantom.
Ok.
Sí.
Dado que eso la observación no lo descarta, al menos hoy,
Ajá.
¿qué pasa? ¿Qué esperarías tú, por ejemplo, desde el punto de vista termodinámico, para un fluido de esa naturaleza?
La verdad, ahí no estoy segura del caso Phantom. No sé si ahí Víctor tiene más. No está Víctor.
No.
No, el punto era básicamente porque tú estás tomando interacción entre materia oscura y energía oscura. Y la energía oscura que estás considerando podría ser eventualmente tipo, no sé, un esquema tipo quintesencia, por ejemplo.
Claro.
Muy
Claro.
bien, pero la interacción eventualmente, no descartable, podría hacer que uno viera, observara, midiera, no sé cómo llamarle, el profesor que recién habló a lo mejor conoce más el tecnicismo, de que este parámetro no, o sea, esté tras el -1, con todas las consecuencias que eso trae, digamos. Entonces, lo interesante es que una interacción que pueda llevar a tener un esquema fantasma es una cosa muy interesante, al menos desde el punto de vista teórico, y desafiante para el observacional. Evidentemente que los problemas termodinámicos son altamente delicados ahí, a excepción de que uno pueda incorporar algunos otros efectos, por ejemplo, esquemas de viscosidad o algo así, que hagan mantener, por ejemplo, la temperatura positiva asociada a este fluido fantasma y, por supuesto, también la entropía. Claro. Si uno lo ve así a secas, va a tener un problema, o acepta que la temperatura es negativa de este fluido y la entropía positiva y viceversa. Entonces, eso es patológico, definitivamente. ¿Okay? Pero puede haber algunas alternativas no desechables por la observación, en la cual ese problema se pueda salvar. Pero lo interesante que veo de tu presentación es que no es esta interacción de la cual hablas para los distintos modelos, no descartan el esquema fantasma, el cual es en sí, digamos, muy interesante de estudiar.
Sí. Sí, no, gracias por el comentario. Y de hecho, en un trabajo que acabamos de también mandar, encontramos que la evolución de la energía oscura alcanza también valores phantom en la ecuación de estado. Sí.
Ok, gracias, Daniela.
Gracias. Qué gusto verlo.
Igual.
Ok, ¿hay alguna otra pregunta? Can you hear other question? Puede levantar la mano o simplemente prender su micrófono. You can raise the hand or on the microphone. Ok, no. Muchísimas gracias, Daniela, por la presentación y esperamos que puedas continuar el día de hoy con el último día del evento. Thank you so much, Daniela, and we hope you continue with this event today. And thank you so much.
Thank you very much. Take care.